movement indicated a increase of the optical path length. We also did things to mitigate other factors such as movement or vibrations, such as index of refraction. If you go to the next slide, and I'll start wrapping up with this, what you see is the displacement of the fringes due to distance away from the spark, the laser beam and the spark. What this indicates, number one, is that there's a 1/r squared type of behavior. It also indicates that there is a maximum movement. And I also oriented the spark in different orientations with the laser, as well as using 2 different wavelengths. And because you see very similar behavior between the two, that began to say we mitigated the index of refraction factor out of the formation of this. So let me just get to some of the applications. I'm looking at propulsion, also communications is an issue, but as others have said, if you think of this as a wave, then you could create a cavity which should give you regions of high and zero gravitational action. So you could create regions of very small, if not zero, gravitational fields. So those looking for low G or zero G type of environments to do their tests, this could be a way to do that if we are dealing with gravitational waves. So I will be publishing these results very shortly, and I am looking to basically create these gravitational waves are called wavelets, and show that this is actually something that we can build usable and functional technologies from. So again, Chance Glenn, Morning Bird Space. You can look up our website, reach out to me via email as well.
Sorry, I was on mute.
Okay, all right. I just want to make sure I was being.
Thank you so much,
Okay.
Chance. This is very helpful, and really appreciate you sharing all that you've shared today. Great to have you, and the important role that you've been playing in EED and extended electrodynamics.
And funded by the National Science Foundation. Thank you.
We're very excited about. All right, so, and I think we have Mark is ready to go from Falcon Space. Mark, do you have your slides ready to present, or Reem, I don't know if you have them handy. Mark's slides came in a bit late. Hi, Mark.
Pull them up. Hi.
Great, and yes, show us. We're seeing your backgrounds. I don't know if you want us to. That's great.
Yeah, that's actually that's what we're presenting about. So you might as well
Excellent.
see it in real life or Zoom.
Are we back on the Are we back on the space one? Or
I think Mark has the slides. You have the ability to project your own slides, Mark, or do you want us to?
It's not on this computer.
Oh no, that's okay. So Rima, I think you have them in the ones I sent on this morning.
Which time slot are we in now?
This was supposed to be in the EED one, the 4.
Oh, stay in the EED. Okay.
4 EED. Yeah. This is, what was it called? Yeah. Try Falcon.
I think it was the last one.
But it's, yes.
Yeah, there we are. Nope.
No, I think we were pulling yours up. Why don't we pull down the presentation? Oh, there we go. Yeah. There you have it.
Is this the first slide?
That's the first slide. Yes, it is.
Just for everybody else who's tracking, this is the last segment. So this 5-minute segment, and then we roll into launch and platforms.
Alrighty. Okay. My name is Mark Sokol. I'm with Falcon Space here in Hawthorne, and we're researching a broad range of alternative propulsion systems that can explain how these flying saucers operate. And this is one of our main projects. It's we call it the Alzaphon experiment. It's based off of the paper from Frederick Alzaphon, Anti-Gravity with Present Technology, and it describes a process called dynamic nuclear polarization, which is a way of orienting subatomic particle spins in order to, in industry right now, this is used to increase nuclear magnetic resonance's signal-to-noise ratio. But Professor Alzaphon theorized that it would actually be connected to inertial mass. There's many different ways of reasons for thinking that this would be true. One of the reasons that Professor Alzaphon thought it would be true is because nuclear polarization, dynamic nuclear polarization, is not a high energy state. It's an oriented state. So thermal processes such as heat and Brownian motion knock the nucleus out of this oriented state. So the colder you make the sample as you're orienting it, the longer the relaxation period would be. But even at near 0 Kelvin, there still is an appreciable relaxation time. And he theorized that the only thing that could be working on it at those temperatures to knock it out of its oriented state would be gravity. So if gravity is acting on this oriented state, then and you're keeping it in the oriented state, then this state of matter would actually be anti-gravity. My favorite way of looking at it is actually, if you look at subatomic particles as electromagnetic energy spun in on themselves, it would kind of be like a top or a gyroscope, which is free to move along its plane and axes. But the subatomic particles in the core of the atom are actually processing around in many different directions simultaneously. And when you try to move a ball through space, let's say you throw a baseball, you're actually shifting the wobbles of those subatomic particles. So that's where the few joules of energy come from when you throw the baseball at the bat. By orienting the subatomic particle spins, you can reduce that coupling or eliminate it completely along the plane and axes of the spin of the subatomic particles. That explains why flying saucers can do a 90-degree turn at 10,000 miles an hour like this, but they cannot do a barrel roll. In fact, many sightings of flying saucers, you see them slowly shifting their orientation to a new orientation before shooting off along the axis of rotation. So this is a very interesting theory, got my attention a couple of years ago. If we go on to the next slide, I can show you guys some of the implementation. So over here we have, these are just a few of the different test setups that we've tried with this experiment. On the bottom right, we have the X-band setup that's inside of our Faraday cage. We're using instead of a waveguide, it was going into a cone, a horn antenna. The center, we have one with a waveguide. On the bottom left with that klystron over there, that is a C-band or like 6 gigahertz setup. And then the one right on top of us, that is the S-band setup. That was actually built by a man named George Hathaway, which many of you may know. And the inventor's son worked on this as well. So this is the S-band or 3 gigahertz setup that I have literally right behind me. We picked it up from Toronto. Now, in the final slide, if you move forward, I can show you some of our, so these are some of our experimental results that we got out of the X-band setup last year. I presented this at the Experimental Nuclear Magnetic Resonance Conference in Asilomar, California. So what you're looking at, most importantly on the right, you see a bunch of squiggly lines that have a sudden drop. What that represents is the weight of the sample over 3 consecutive runs superimposed on it, on top of each other. So there's a clear signal being seen over here. It's not very strong. It's about 0.75% of the total mass of the sample. And it's happening right around the Larmor frequency or the gyromagnetic ratio. That's where this effect is expected to take place. So we're very excited about these results. There are different methods to increase polarization. And if those work out the way we expect, we should be able to make VTOL, vertical takeoff and landing craft, from Earth to space without any rockets needed. And that's the end of my presentation.
Thanks so much, Mark. Really appreciate you sharing your experimental results and your approach. Very, very interesting work here. Great to see you.
Thank
All
you.
right. So next we will transition into the launch and platforms side of the day. And just for those who are tracking, we've kind of been running about 15 minutes behind all day, but we've got some smaller segments, I suspect, at 4 and at 5. So I think we're going to start running earlier after this launch segment. So, and here we are with Stoke Space. Do we have Devin on?
Hey, I'm here. Thanks so much for the opportunity to be
Devin,
here,
great
Anna.
to see you.
Great to see you.
Excellent.
Well, I can dive right in. Thank you again, and appreciate the opportunity to chat with everyone. We're Stoke Space. We're building 100% reusable rockets designed to fly daily. Our founding thesis is that if you want to be successful, you have to think about the end game before anything else, and then work backwards. And inevitably, to build and realize many of the really cool products and capabilities we've been talking about today, that end game is fully reusable rockets operating at a very high cadence, like a commercial airliner, moving to, from, and through space at a very high cadence. So we're designing with that end goal in mind. We are building a 2-stage reusable rocket. Stage 1 is akin to the Falcon 9, vertical takeoff, vertical landing, either downrange or launch site. Stage 2 is our big differentiator. It goes to orbit, it deploys payloads. It can hang out, loiter, and maneuver on orbit for some time. It can grab payloads that are already in orbit, maybe staged in orbit, or assets we want to get back. Once it's done that, it re-enters the atmosphere, it deorbits, re-enters base first like a capsule, like Apollo or Dragon or other space capsules, and then lands propulsively at the launch site or elsewhere as mission requirements demand. And one of the, perhaps the biggest challenge of coming back from space to be fully reusable is surviving atmospheric reentry. And we have a secret sauce to do that on the next slide. Developed in part with NSF funding, so we're very excited and grateful for that. We built this, which is our integrated heat shield and upper stage engine. They are one and the same. If you look at legacy traditional approaches to bringing things back from orbit, so think the Apollo or Dragon capsules, think the space shuttle with ceramic tiles, we typically use ablative heat shields, which are one-time use, or we use very fragile, brittle ceramic insulators like the tiles on the belly of the space shuttle. And the problem we see with that is that it has catastrophic failure modes, as we saw tragically with Columbia, which a tiny piece of foam damaged a single tile, hot gas got in, and it led to a very bad day. And we want to operate like a commercial airliner. So we want to think really, really hard about all the things we're not doing in between each flight. So we're probably not visually and X-ray inspecting 30,000 tiles for a tiny crack or flaw. We want to be able to land this thing, refuel it, refit it with a new payload, and refly it again in a very, very quick cadence. So we said, look, how do we get over this reliability problem and build something that is robust, rapidly reusable, and we know it's going to operate successfully on flight 2, flight 10, flight 1000. And as an industry, we have been actively cooling rocket engines, the nozzles, the combustion chambers, other parts of the engines that would be susceptible to high heating and melt very, very quickly. We've been actively cooling them with cryogenic fuel. So we're flowing, in our case, cryogenic liquid hydrogen through channels in components, and we keep them cool. And this is a proven, reliable, robust, fails passively method of making rocket engines. And as an industry, we've done that for decades. So we said, why not apply that to the entire base of the vehicle and make an entirely actively cooled heat shield? And so that's what you see here. What you see around the circumference of this heat shield are a thrust ring, are 30 liquid hydrogen thrusters, each producing about 1,000 pounds of thrust. They're all fed by common turbo machinery, which sits inside that actively cooled heat shield. And then what you see is 3D printed panels. There are many dozens of them that are manifolded, welded together, that form the propellant or the fuel feed system for those thrusters. So liquid hydrogen is flowing through small channels that are 3D printed, developed in part with NSF funding, out to the thrusters. So that keeps them cool and ascent, so the engine doesn't melt when it's going to space or maneuvering through space. It also protects it when it's coming back from space. So we're able to flow hydrogen through channels in that heat shield, absorbing the heat of reentry, and then dumping that overboard. When it lands cold, and it is ready to be flown again, because it's a known thing in industry. Both there are public examples on space shuttle main engine, as well as more private examples of actively cooled, regeneratively cooled structures successfully operating with known flaws or cracks. Those cracks are categorized, tracked, and eventually maintained after 10 flights, 100 flights, 1,000 flights. On the next slide, we can show we've actually flown this thing. This is a full-scale prototype of our reusable upper stage. It's about 5 meters in diameter at the base there to give you a sense of scale. And back in 2023 at our private test site in Eastern Washington, we did a vertical takeoff, vertical landing hop flight of this full-scale prototype, which included that very unique engine and heat shield. It was a number of industry firsts, which we're really proud of and excited about. One of the cool things about this engine is rather than using gimbals to provide thrust vector control, we don't gimbal the engine, we use differential throttle to create our pitch and yaw moments, which saves weight and complexity. And we think we're one of the first companies or first rockets of this scale to demonstrate that. It was also, first demonstration of this type of heat shield approach. And we were proud of very rapidly going from a company with seed funding and some NSF grants to flying a rocket even in a low altitude hop. That's all I've got so far. Would love to chat with anyone further if there's any other questions.
It's just it's just great to see how much you've done in such short time. So I was there with the first proposal, and having been the first funder of Stoke, it's just amazing to see. And Andy, often shared that there were challenges, in terms of just getting there, in terms of all these different areas. There's always, but your team has really done so much in a really short period of time, and NASA came in and was supportive very quickly thereafter. And I know you've got some great DoD supporters as well. Are there other agencies that you would cite that you've worked with?
I can say that there's others in the intelligence community that we're honored to work with, but very happy for all of our government supporters.
Well, we're thrilled to see the progress. So thank you for sharing.
Thank you.
Okay, next up. Let's see, flip to the next slide. We have here, because I think we have. Do we have John Roth on? Hi, John.
Yes, Anna. Hi, everyone. Hey, Anna.
Great to see you.
Thank you for having me here. I'm kind of going to change speed a little bit on some of the other presentations, into fact as
John, can I help bridge that for you? So I guess we're delighted to have you here. And just, as one of the things that we're seeing is just this tight connection between launch and platforms, and then what's driving that demand, what do you need it for, right? So that there's tremendous opportunities across many of these sectors, be they biotech, advanced materials, satellites, so many of these different areas. So really grateful that right here in this section on launch and platforms that you can share kind of what this very large community that you're the nexus of. I think you can share the number of participants if you care to, but there's so much momentum in this area.
Okay. Well, thank you for that, Anna. I'm here to talk about road mapping that is currently going on. We put in a proposal a couple of years ago to roadmap in-space manufacturing, which then got broadened out into in-space service assembly manufacturing, but not from a NASA and a DoD perspective, but to roadmap it from a sustainable commercial-based space-based economy. So it was to say, what will it take and what does industry need to make a business case and a sustainable model for operations in space? The objectives of the roadmap are to identify the technical barriers and the knowledge gaps that currently exist that are preventing us from doing a space-based economy. For each of those, to identify the TRL levels for both the research and then the commercialization opportunity. And then from there to develop and look at the deployment of it over a 10-year horizon. And that's an important thing. Things that are beyond 10 years are considered with respect of what needs to be enabled within those 10 years, but it is chopped off at the end at 10 years for this particular roadmap. As I mentioned, it's supposed to be from the industrial and commercial perspective. We held workshops across the United States. There were quite a few of them. A vast majority of you here that I see names of have contributed at different times at different levels. So you're somewhat familiar with this already to begin with. Some of the alignments that we were told to make was to make sure that we are aligned with the current transition from government-owned assets to commercially owned assets. And then also a large push was to make sure that as we look at a space-based economy, it is only, or let me say, not only accessible to large companies, but there are mechanisms that allow our current and thriving startup and small, medium enterprises to remain competitive in a space-based economy where they're not overweighed by the investments that other larger companies might be able to make and that they cannot. Next slide, please. So when we convened everybody, we had, I guess, across all of them, to answer your question, Anna, several hundred, I think we're close to around 500 total people that came to the various workshops. And then we've had input outside of that from various companies. We allowed them to scope out what we are trying to do in a lot of different ways. They did first the scoping. Obviously, as part of the road mapping for in-space manufacturing, there's going to be the design, the materials, and the manufacturing processes. But what got added in is road mapping product launches and services, how national security and security of assets, two different things there, play into the larger picture. What we need to do for workforce development and knowledge, skills, and abilities to be able to enable this sustained space-based economy. And then what are the supply chains that we need to facilitate and operate ISAM? So not the supply chains necessary for all the launch that we're currently doing, but if we're really looking at in-space manufacturing, what does the supply chain look like? Within that, we have to do bounding of the roadmap, which is we're basically going through the lunar orbit, Mars is beyond it, applications were space and Earth, and we have to look at the products. Some things really quickly on that. Mechanical, electrical, and biological systems, including pharmaceutical, are all part of it. The chemical fuels and power were taken out. They decided that is outside of scope of what they wanted to roadmap, so that is removed. An inherent value assessment was done of what is the business model, what is it when it, or how long is it till it is revenue generating, and better yet, profit generating. How do we reduce the Earth dependence, and how do we minimize the environmental impact? From that, we came up with a variety of topical roadmaps. There were 82 of them in the end. And we put those into different areas, looked at use cases and the considerations for them. And then last slide, please. Then we looked at and identified where they were looking at the impact areas. None of those are very surprising. We've been hearing them all day. National security, strategic readiness is on the list, global communications and operations, medicine, biological wellness, all of that's been in there, exploration, discovery, and then obviously our space, weather, environmental monitoring, things like that. Capability gaps, the largest ones, we are missing space infrastructure that would allow in space manufacturing. We are missing the logistics structure that allows it. We are missing refuel, repair, and reuse, and then all the rest of the R's behind it. And then how do we test and validate that? Finishing up, the last thing we want to say is we are continuing to work towards funding models. In the current budget, right now in front of the House, there's money for an in-space manufacturing research center and also for an institute. We will continue to pursue those. We are also trying to pursue opportunities for a larger investment strategy that would be a CHIPS level investment. On that, thank you very much for your consideration. The roadmap hopefully will be coming out for agency review in January and then for public review in February, March, with then a report out to Congress in late March is our current planning. Thank you for your time and attention.
Thanks, John. I just want to make a quick comment since I'd worked with you quite a bit over the time on this. It is important that the final report to the NIST Advanced Manufacturing Office is fairly imminent. We're finalizing it right now, but the other thing is pushing toward that center of excellence. I think if that can happen, we'll go a long ways towards starting to pull together a coherent roadmap and start pulling together standards and other things such as that. So thanks very much for all this effort and the organization.
Okay. Thank you, Curtis.
Going to say the compelling need, to advance in these areas. So thank you, John, for all you're doing. But driving it back to the comparison with terrestrial infrastructure, and when Curtis says we need centers of national excellence, just think about the scale we have for some of these sectors terrestrially, and we need to be engaging, in that capital availability, those capital formation tools, and certainly, workforce, all these areas to scale, this competitive advantage and opportunity in space. Okay, then next up, do we have
Anna,
Lucy on?
can
Yes,
I add just one real quick thing there so
please do.
people, I mean, I appreciate you emphasizing that on the Centers for Manufacturing Excellence. Just so that you're aware of it, under President Obama, there were these Centers for Manufacturing Excellence were originally established. Each one of them is initially funded with $700 million of government funding, and then over a period of time, they become self-supporting. The one that most people are familiar with is America Makes for additive manufacturing, but we have a large one called NextFlex that some of you have worked with for flexible hybrid electronics. We want to get one for in-space manufacturing. So it's a big potential thing that could happen in the near future.
If I could add to that, it actually is in currently the House subcommittee's budget for that institute, as well as the Center of Excellence. So there's one for the Research Center and for that are both in the House budget right now. So hopefully it will make it into this year's budget.
Well, thank you for sharing all of your work. Do we have Lucy here from Axiom? Hi, Lucy. I know Lucy was on earlier. She might need to step back in. She might be. Oh, I see her.
Okay, can you
It
hear me?
doesn't look like Hi, Lucy.
Hi, sorry, I was just getting my microphone sorted there. Hi, thanks for pulling together such an incredible day, Anna, and the whole team. Really excited to be.
Talent is out there. You all are out there, and we know you're eager and willing to share. So much appreciative of your work, Lucy, and that of others.
Absolutely, yeah, I'm absolutely delighted to be here. So I'll jump straight in with my 5-minute segment. So really excited to be amongst such an illustrious group of incredible disruptors today. But as Anna mentioned right at the beginning of the day, the space industry is really an area of massive convergence of so many different kinds of transformative and innovative tech. So at Axiom, we are a company that is building a space station. So we're essentially technically a space infrastructure company. I'm going to talk a little bit about a couple of the things that we're doing, but we were asked very much to focus on how we are disrupting the new space economy. And so first slide here is really just highlighting what we're doing as a broader company for our vision and mission. So our vision is really to transcend Earth. So really to start taking advantage of these incredible opportunities that are afforded by doing research, manufacturing, exploration in space in the coming eras. And our mission is to build an era-defining space infrastructure that drives this exploration and fuels a vibrant space economy for the benefit of every human everywhere. So if we can go to the next slide, please, then what I'm going to do is talk about some of the disruptive technologies and the opportunities that we've been embracing at Axiom. So this slide is a representative of some of the focus areas that we've been working on. And so some of the areas that we're very focused on as a company to develop these economic opportunities in space is in space manufacturing. So this slide is very representative of some of the biomanufacturing we've been doing. And we had some fantastic presentations earlier on this morning from Kat Jamieson and other teams that we've been working with that are looking to exploit the environment of microgravity to do research that can transform potential opportunities here on Earth. So we have 3 companies or 3 teams, for example, that we've been working with that are actually also funded through the NASA INSPAR program that is looking at biomanufacturing in space. So looking at the development or the self-assembly of DNA-inspired nanomaterials, looking at doing the proof of concept studies that are important to understand what stem cell manufacturing might look like in Earth. And then also looking at the possibilities and opportunities for bioprinting tissues in space as we move towards developing products that can be made in space that could transform healthcare here on Earth. And so excuse me. And so Curtis rightfully gave me a nudge when I sent these slides in, and he said, oh, hey, but Lucy, Axiom is doing so many other things as well. And that's exactly right. So some of the other aspects that we're working with has actually been highlighted by some of the companies that presented earlier on today. So Single Crystal Diamond and United Semiconductors, we've actually been working with those teams as well to be doing some of those important proof of concept studies to start building towards those opportunities to be doing things like manufacturing of semiconductors in space. So we appreciate, obviously, I think everyone on the call probably appreciates by this point that crystals form differently in space. And so we plan as a company to be really embracing those opportunities and building those economies to then provide a platform that can manufacture these kinds of products at scale and then transform industries and transform technologies back down here on Earth. Next slide, please. One of the other ways that we're planning to be disrupting the industry, excuse me, is actually we've got the contract to design and build the next suits that will be used both on the lunar surface and now also for future EVAs, extravehicular activities in future. So while everyone has known about spacesuits for donkey's years, and NASA's obviously been developed and used them previously, and they've kept crews safe and healthy in space for many, many years, the opportunity to develop the next generation of this has meant that we've been able to really pull in some incredible partnerships from some of the world's leading commercial experts on things like visor coverings, on some of the textile manufacturing that we're using to actually, excuse me, cover the spacesuit. We teamed up with Prada, for example. So Prada is obviously a fashion designer, but they have incredible generations-long expertise in things like how you actually join different layers of different kinds of materials together. They have expertise on static control, which is incredibly important when you're looking at things like how to deal with lunar dust and the static issues of that. So we have been partnering, like I said, with many different organizations to offer things like advanced radio and communications opportunities, some of the different technologies we're looking at for environmental control and life support within the suit, which has to be a self-contained spacecraft, essentially. And then also different kinds of, like I said, textiles, visors, all kinds of communications technologies. So that's my time up. I'm happy to take any questions in the chat, and thank you again for the opportunity to take part in this incredible day.
Well, Lucy, thank you so much for your time and expertise, and it's really impressive to learn about the work and just the broad spectrum of opportunities here and work that needs to be done. I see Curtis is coming on, so I'm sure he has something to add.
Well, just a quick add that Lucy mentioned the semiconductor aspect of it, but Axiom is involved in such a broad width of work right now. It's almost hard to believe. It seems like everywhere I look, they're on a different project, but that's a good
Very
thing.
busy.
That's a good thing. They're active in the space, so to speak. So we appreciate you guys and the work you're doing, Lucy.
Thank you so much, Curtis. Really appreciate it.
I think we have, if we flip to the next slide, please, Rima. And I just want to say with gratitude that Ken, did all the preparations to join us here today, and we're thrilled that Sierra really has been part of the day today. He had an issue come up for which I don't believe he's still on the line right now. Ken, are you on?
No.
I think he had something come up, but he sent his regrets, and he was certainly very much a part of the planning for this day. Curtis, I don't know if you or Kevin had anything that you wanted to share about the work with Sierra.
No, I will just comment. I mentioned this earlier when United Semiconductors was speaking this morning, but Sierra Space has worked with several of our companies, both in semiconductors and in bio, to look at the potential for their inaugural flight of the Dream Chaser vehicle. We're hoping that does happen in early 2025. It would be a great capability for us to have as a working economy. So many of you may not be aware of it. It's a reusable, returnable launch vehicle. It's looks kind of like a super updated space shuttle, but it's a neat vehicle. I wish that Sierra would have had an opportunity to present.
Thank you. All right, so let's move past the Sierra slides to the next presenter is going to be, let's see, we've got Vast up next.
Great. Thanks all, and thanks for appreciation and our opportunity to present here. I'm David Caponio, Senior Vice President of Product and Business Development at Vast. I'm here to talk to you about Haven 1 and specifically our laboratory capabilities on the first space station here. So what is Haven 1? If you haven't heard about it, haven't been on our website, Haven 1 is scheduled to be the world's first commercial space station. We're planning to launch for the latter part of next year. With that, Haven 1 will be a single module space station consisting of a 3-year lifespan. And we plan to crew those in 4 individual missions of 10 days each. So approximately with the ascent and descent with Dragon, about a 2-week mission in total. We made it as big as we possibly could. It fits a Falcon 9 fairing, kind of standard launch return to launch site, of 45 meter cubes of habitable volume, which is about 5 times of what Dragon is today on those free flying missions. So Drop Dragon, we're about 6 times the size of a typical free flying Dragon mission. We have sleeping quarters for 4, so it's a total crew of 4 that goes up in the Dragon and then lives and works in the Haven 1 space station. We have a large wind dome. You can see that on the picture there for viewing the Earth. We have a large kind of communal working area with an extendable table for dining and for working on the laboratory. We have a large high bandwidth link with Starlink connectivity in the space station. And then we get into our, what we're going to do with the laboratory. So we, since this is operating in parallel with the ISS, launching next year, we've taken the SSP 57000 standard and we've built pretty much a full express rack type of capability. So that's 10 mid-deck locker equivalent spaces within the laboratory. You'll see that on the next slide. Let's go to the next one. Yeah. So the Haven Laboratory, like I said, 10 mid-deck lockers. We have the ability to double up there too. So some of the payloads we're looking at are double mid-deck lockers as well. And we've kind of done it on a commercial partnership basis. So we've announced our first 2 commercial partnerships, both the first being Redwire and the next one, a European provider called Yuri. And then we have the next 4 reserved for other commercial partnerships as well. And then the 4 themselves and the last 4 mid-deck lockers are actually reserving those for the 4 individual crew members to curate their own missions and do the research and science manufacturing that they want to for their particular mission. That's also interchangeable. So we have a small cargo capability on the Dragon mission on each of the 4 missions, so we can bring up both refresh payloads and bring up entire new mid-deck lockers. And it's very similar to what you experience on the ISS. So we do have conditioned storage as much as we could. We have 30 kilograms per locker. There's 100 watts of power being supplied. That data and commanding link, like I said before, via Starlink as well, and it is our RF and space, our ground and RF space links as well. And then we had that commercial product return. So with the Crew Dragon, we have about 200 kilograms of payload capacity up and down on each of those missions. One a key element too with the laboratory is that for the first time ever, there's almost little to no commercial restriction on what can actually be produced in space. So, typical on the ISS, an incredible laboratory space, but they're most of the time the partners are prevented from commercializing or selling their product when they get back down. So Haven 1 Laboratory essentially becomes the beginning of the LEO economy, the first time where you can actually develop a business plan around crewed microgravity environment, develop products, research products for particular profit interests, but the first time we can actually realize a business interest in space in a crewed environment. So that's a pretty special element of the laboratory itself. And then the final slide we can go to. What we'll be doing next? We announced this back at IC back in October, a few months ago. We announced our architecture for the commercial LEO destination. That is what a space station we call Haven 2. It builds upon the architecture of Haven 1. So it's a stretch module. We're using a Falcon Heavy stretch fairing architecture. So pretty much an existing launch architecture that we don't have to wait on. We're launching the first module by 2028, the start of the CLD program, and ensuring no gap to the ISS and actually an overlap with the ISS. That first module will be crewed just like Haven 1 is with a crew of 4. And then we add 8 additional modules through 2030, through the end of the ISS, and fully built by 2032. Each of those modules adding increasing capability for life support, increasing capability of livable area and power and thermal control with the space station, but also increasing capability in an iterative fashion for those laboratories facilities. So much like on Haven 1, where we have 10 main deck lockers, we'll have double the capacity on each module on Haven 2, and each module that is launched will essentially be adding more laboratory capabilities to the space station architecture as a whole. We're also excited about Starship coming online. We develop a module that's about 6 to 7 meters in diameter, so a high livable area and a high mass capacity by using that launch architecture when it's online. That becomes the core element of this kind of ring of 9 in a star formation. In total, and 9 modules in total, with 611 meter cubed of buildable volume, 86 kilowatts total power, will eclipse the ISS in capability, not only on capability total power in the station, but also capability in power and usable area for the payloads themselves. So a laboratory better than the ISS. And then just like every CLD provider, having a mixed use, both government utilization and commercial utilization, even from day one. And the important thing about this CLD architecture is that with Haven 1 launching it 2 years prior, it will be launched on the back of heritage of an already operating space station. So all the TRL level will be raised, all the risk will be retired as much as possible, and effectively will be building on the heritage of Haven 1. So that's our plan, both in the near term. So payloads getting signed up, in the next few months to complement Haven 1, and then looking beyond for a CLD program and replacing ISS with a giant world-class laboratory for the US, Europeans, it's like Middle East, Japanese, and the rest of the world to join in on as a successor to the ISS. So that's all I got. Any questions in the chat? Welcome to field them. With that, we'll hand over to the next presenter. Thanks very much.
Thank you so much, and it's really just exciting to see the potential to build, much more of this capability for these space stations. There's been so much that's been done already on what, people who aren't in space don't realize that the ISS is the size of a few small houses. So the importance of getting to that infrastructure scale and all those tools and that capital to be able to build out as many of these as researchers, business people, tourists, whoever it is, would see the opportunity to build. So really appreciate it.
Thank you.
Thank you.
Appreciate it.
So next presentation, could you flip the slide, please, Rima? Rima, you've been amazing. You're the the hero of the day. Is it still
my
Rima
dues.
flipping slides? Rima just still flipping slides. Amazing. Max, so grateful to have you here today with Rocket Propulsion Systems.
Hey, Anna, actually, this is Ankur. I'll be presenting for
Ankur.
RPS. I
Great
think this is
to
the
have
first
you.
time
Thank
we're
you.
meeting you. Yeah, great to meet
Thank
you,
you.
and thank you for putting on this all the events today. So, yeah, Rocket Propulsion Systems. We're based in Kent, Washington. We are essentially looking to streamline transportation in space, specifically targeted to payloads roughly 200 kilograms or less. So when I say space transportation, on the screen here on the right-hand side, we have what's called an orbital transfer vehicle. An orbital transfer vehicle is something like a space taxi or a space Uber, you can think of, in the same way that an Uber is a cheap, reliable way to get around any city or any area. You can also think of it the same way the subway connects people across New York City, for example. Our orbital transfer vehicle will be able to transport quickly and rapidly and cheaply assets all around space. So we'd like to be transparent when we say low cost, we mean it. This entire orbital transfer vehicle would sell for roughly $1.4 million, and that price is definitely destined to come down in months and years to come. And the engine, for example, has a weight of 33 pounds with a thrust of about 100 times that, utilizing LOX methane propellants. We basically want to be able to utilize our OTV to service payloads such as satellites, commercial and defense satellites, as well as experiments in manufacturing processes like those conducted by all the different types of companies that we heard earlier on in the day. Biotech companies, advanced materials companies, as well as semiconductor type companies. So we'll move to the next slide. And I'll start off by, on the next slide, I believe, talking about some of the defense applications for the OTV. So naturally, a technology like this can be utilized to transport defense satellites, defense payloads, defense sensors to different places in space. So one of the particular missions is what's called LEO to MEO, low Earth orbit out to medium Earth orbit transfers. That's roughly a 300 to 400 kilometer start point and a 15,000 kilometer endpoint. And we would be able to transport payloads over this distance in about a day. So currently AFRL, Air Force Research Laboratory, Space Systems Command, as well as US Space Com are particularly interested in this. And why are they interested in it? Well, in large part, LEO, the 300 to 400 kilometer distance, was the biggest problem in operating new satellites in LEO was just space debris and space junk, given how crowded LEO is becoming. But as of recently, we know that adversaries to the US are developing weapons in space up to and including potentially nuclear-based anti-satellite weapons that threaten a lot of the defense payloads in LEO. So being able to quickly and rapidly transport these payloads to a safe place where they can perform reconnaissance, surveillance type missions is becoming more and more needed. And AFRL is recognizing that, and therefore a constellation of such OTVs, these in space, would be able to basically loiter in space and quickly attach on to any defense payload and rapidly move it out to a safe place. So on our OTVs will be propelled using LOX methane propellants, and we have a fluid management system on board, which will allow us to keep these propellants at temperature for months on end, and basically prevent boil off, which is one of our secret sauces that we want to bring into this technology. We can move on to the next slide, and I'll talk a little bit more about the ISAM, the in-space assembly and manufacturing capabilities that we would like to support. So this orbital transfer vehicle will be one part. Rima, do you mind going back one slide? Thank you. So this Rima, do you mind going back one slide to the orbital transfer?
Sorry,
No worries.
too many windows open.
No worries at all. I understand. Thank you. So this OTV, this orbital transfer vehicle, will be one part of a complete launch platform that RPS will develop. The launch platform will consist of rockets, a two-stage rocket, the lower stage and upper stage, both consisting of LOX methane propellants, lower stage consisting of roughly 6 engines, and the upper stage, which is essentially what the OTV is, consisting of that one engine. We will also have reentry capsules, which will basically act as or be a payload on our OTV, in which we can host manufacturing processes, biotech manufacturing processes, crystal growth, advanced material growth, or we can also utilize our OTV to transport such processes to in-space space stations or habitats, such as, for example, what I believe Radiant Space Systems was building early on. They were building habitats in LEO to be able to perform in-space manufacturing. Our OTV would be able to basically transport the payload to their habitat. The payload would enter their habitat. They would perform the ISAM. the ISEM, the final products would then be transported or be put back on our OTV, and our reentry capsule would be able to bring those products back down to Earth and return to the customer. So, like we've mentioned, I don't need to spend too much time on this. 3D printed human organs, novel medical drugs, fiber optics, crystal. These are all different types of manufacturing processes that I believe would fit in that roughly 200 kilograms or less, which our OTV for a low cost would be able to either host or transport to a final destination. As a final point, blockchain and cryptocurrencies, I'll mention a little bit on that too. So right now, mining of cryptocurrencies like Bitcoin and others is becoming more and more of a field that requires high energy power for data centers. Well, our OTV would also be able to transport a portion of these data centers, if not the whole data centers, up to these LEO and MEO orbits, where through our solar panels, we would be able to provide essentially infinite power or more than enough power needed for cryptocurrency mining. So we are currently also looking to be able to partner with any companies looking to mine Bitcoin or other companies as a power provider. So thank you very much. Appreciate you listening.
Thank you so much, Anchor. Great to see you. And definitely a lot of very exciting areas you're talking about here. And then also just what some of the work you're talking about is very transformative economics as well. So really appreciate what you're doing to drive down the cost here.
Thank you, Ann.
Yeah. And so I think we're fortunate to have Leap who joined in today. And Leap, I think, has their slides ready to present. Is that right? Can we give Adam the opportunity to present? Thank you. We're back on time. Who would have thought All right, Adam, please go right ahead.
Hey, can you guys hear me? It's not letting
We
me
can, thank you.
share my camera.
That's great.
But I'm here. Give me 1 second. I'll see if I can get the camera working, but otherwise, no worries. Yeah, it's not working. Cool. So we are Leap. We are also providing logistics to, through, and from space. So a lot of similarities here with some of the other companies that you just heard from. We have you guys can see my slide?
We can, yes.
Okay, perfect. Just making sure. What we have a really novel engine technology. So what we've done is we've combined a booster engine and an upper stage engine into a single unit. So we can make simpler, more reliable vehicles. The whole thesis behind this is high reliability and reducing complexity. So we've done a bunch of engine testing. We've had this engine validated by both NASA and AFRL and the Air Force. So we've just basically gotten through that part so far in Denver. What is this good for? We can use this in a bunch of new technologies or existing technologies. We can make simpler launch, more highly mass producible launch. We can make space planes. We can do targets, hypersonics, next gen interceptors. So we kind of making everything simpler with our rocket engine here. For an example of that, like a practical example, Rocket Lab, Electron, they've got 11 engines, 3 stages. We can deliver 1,000 kilograms to LEO with a single engine, single stage. And that's our Springbok vehicle pictured here on the right. It's just a rendering. I know it's a really good rendering, but it doesn't exist yet. It's about 2027. We're going to be bringing that online. So here's a few of our applications that we're working on. Outside of the ones I already showed you, there's a lot of areas, but the ones we're pursuing are in-space manufacturing or point-to-point with our Jerboa in-space platform. We have a high delta V OTV that can do LEO to GEO in 5 hours. That's really important for, as the previous presenter was explaining, high reconstitution speeds for military assets. We're doing a suborbital vehicle, an orbital vehicle, and then the end future goal here, the dream is to do a fully reusable space plane, kind of like what Sierra is doing, but it's a vertical takeoff, horizontal landing, and that can pretty much do everything here. And service commercial LEO destinations. Take products to CLDs like Axiom, Vast, Sierra, all those guys. So the two or three that I put together here just to show you guys today is our in-space manufacturing platform. This is a 300 kilogram of down mass, so we can put this into orbit. We can do a loiter time of 2 hours to 2 years if people want. Again, we're just engineers building a platform. We're not research scientists, so we're just looking to collaborate with people. Shout out to Kevin Engelbert. Thank you so much for just working with you so far on some of this stuff. It's been super helpful. You guys' whole team has been great. But yeah, so clean, pressurized, high microgravity environment. It's like a mini ISS, 8 locker configuration on orbit that can be called down at any time and land. Our suborbital vehicle is, again, it's just for providing a platform for researchers, atmospheric, hypersonic testing, microgravity. We can do 10 to the minus 6 G for 2.5 minutes, 100-pound capacity. We can do Mach 7 trajectories. So again, our whole goal here is to use our technology to enable platforms that allow you guys to do research, or a lot of the people that presented earlier today to do that research at a high cadence. Right now it's hard to get to the ISS. We want to do it quickly, cheaply, reliably. Like Lambda Vision was saying, it took them 9 years or so far, or 6 years so far, 9 flights. It takes a long time to do this, and if you can have access to a platform that is has high cadence, maybe you can get some of this research done quicker, accelerate some of these products to commercialization very quickly. The last one I have here is just this is kind of our flagship product that we're bringing online. 1,000 kilograms to LEO. Again, single stage to orbit, single engine. By removing all the stages and all the parts, we want to provide everyone a really cheap and reliable platform to get to orbit. We know it's hard for companies to get to space right now. There's long wait list times. Rideshare doesn't really take you where you want to go. There's a lot of problems. So again, we're just coming online, and hoping to work with a lot of you guys in the future. Cheers.
And really appreciate all your sharing here, and also just as you've spoken to the importance of really increasing that cadence, that frequency, that access, reducing the wait times. These are definitely things that many of us are speaking to as major challenges. So all of these solutions to really increase the access are very, very important. And just this contrast between today, leading capabilities still meaning waiting a long time, versus leadership is really going to mean being able to iterate and to build things, produce things, manufacturing things at the speed of innovation and the speed of production for products. So we really do need to, as an ecosystem, ramp up the in-space capacity that we have. So lots of moving parts to get that done. Thank you so much, Adam. Okay, so I think that was the end of this segment, and we're very close to back on time. And I suspect that we might even quickly get to being ahead of time, because our communications segment is a little bit, has a few less presenters in it. And a couple of logistical issues have come up for at least one participant as well. So I think that we might even be able to, I would expect, move into the quantum presentations before the 5 p.m. timeframe. So for those that are in quantum, please do realize we'll probably want to free people up early today. And so let's move right into Rima, the comms deck. Are you able to keep flipping? I know this is a lot.
Yeah, this should be the comms one now.
I think this is,
It's 8.
no, is it?
Yeah, it's 4.
Is this the it could be, this might be the comms, because there are more EED people in the comms group. So this was Charles's presentation, so that's EED. So this
That
is
looks
the
like EED, yeah.
So this
boy.
is yeah, this would be the group that I think it's 8. I think it's 8 is comms.
Mm.
And just for
That's-
those that are in that group, we're expecting that the presentations are going to be on space. So we'll see Philip and Javier. So we'll see Anchor, and then we're hoping to have Chassis on as well. And then we might have US Air Tech as well.
Uh-oh. All right, let me go back to the Google Docs. I think it got
Yeah,
mislabeled.
we can also send it to you. Philip, do you have your
Hey,
slides ready to pull up? Yes, Diane?
yes, ma'am, I
Just
can do that.
Oh, okay. I was going to say that Chassis is going to be presenting their slides on their side due to the animations. So if we need some additional time for Rima to locate the current file, then Chassis can also provide some
Great.
assistance.
I'm checking the Google Docs and it's the same. It's the very
Yeah,
first.
we can resend it to you, or we've got enough time in the slot that everybody can present their own as well.
Okay.
So it looks like Philip's got his up, so that's great. And thank you, Rima.
Well, hi. Yeah, I'm Philip Lentz. I'm a co-founder and researcher at Unspace. We're focused on gravitational wave communications. And I wanted to say thank you. It's been very inspirational being part of this today. On September 14th, 2015, LIGO detected gravitational waves. And on this day, we stretched the boundary of what's possible for small scale measurement technology. LIGO can clock in at 1/10,000th the diameter of a proton. But even more important was the development for the possibility of future gravitational applications. LIGO informed us that Einstein was right again, that space and time are stretchable, it's alive, and we can do things with that for applications. It also confirmed that the interaction of gravitational waves with matter is incredibly weak. It takes 2 4-kilometer long arms to detect gravitational waves. So it begs the question, how could that be used for communication? That's not going to fit in your back pocket. So as such, there are communication problems that can be addressed in space by gravitational waves, and we'll come back to the how in just a minute. But solar and terrestrial weather interfere with communications, the ionosphere interference, radiation, space debris, disruption of relay satellites, signal latency from relay satellites, astrophysical bodies will occlude communication, rotation of planets prevents communication with colonies on far side of planets, far side of the moon. Also, icy planet communications with landers, with space probes that are underwater would benefit from such a technology. But yeah, how could LIGO's large-scale infrastructure be reduced to a form factor that's practical for communication? We talked about it a little bit on this slide. An investigation into the less understood areas of general relativity kind of paves the way. Specifically, experiments that investigate the directional or anisotropic components of GR. It took 3,000 years for Einstein to stand on the shoulders of giants like Kepler and Galileo, Newton and Maxwell to create our best theory of gravity. But the universe teases us and tells us that he's not exactly right either. We see that pulsar frequencies exceed their breakup expectations. Stars in the outer bands of galaxies, they orbit their central black holes faster than our theories can predict. Gravitationally assisted space probes, they experience anomalous accelerations. UAPs instantaneously, we've talked about this all day long, it's been so fun. Change direction at Mach numbers that should produce inertia that would just tear them apart. So many of these things suggest an anisotropic property of gravity. And that's what we're doing in Unspace. We're investigating that. We've built an experiment. It's called EGAD. It's the Energetic Gravitational Anomaly Detector. It's about a $2 million experiment. We received phase 1 support from the NSF. Thank you, Anna and the NSF. And 2 years of experimentation repeatedly have showed that centripetal stress energy produces a directional gravitational field. In novel ways that allow applications that we previously thought impossible to produce useful benefits for us. So what are we doing with this? Well, our job at Unspace is to understand and characterize how these anisotropic fields can benefit applications, specifically communication. So we're working on a prototype to utilize what EGAD has taught us about these changes directionally with gravitational fields. One characteristic is they obey the inverse. They do not obey the inverse square law. When we start looking at stress energy and its effect on space-time, it becomes a inverse single power law, which coincidentally means that these stress forces or gravitational fields become the dominant force over intrinsic mass energy gravity at distance, which explains the galactic rotation curve problem. So what we do is we use this property to create an artificial gravitational lens that curves gravitational waves, like the way an astrophysical gravitational lens enables telescopes to see light from otherwise unseeable distant stars. We use this lens to shape space-time in a certain way that concentrates artificially produced gravitational waves into a focused beam. And that beam reaches a higher energy level that's detectable by a small scale interferometer at a sub-meter size form factor. But that's not very useful for communication unless we can modulate gravitational waves and encode information. And to do that, we need to produce a broad profile generator of gravitational waves. We can do that by changing modes of angular acceleration of rotational masses. Using this approach hints at broader cross-functional impacts as well for geophysical sensing, gravitational propulsion, and controlled remote displacement of objects that can be used for Earth-based satellite deorbiting. And yeah, that's what I got. Thank you, Anna.
Thank you so much, Phil. Philip, it's great to see you. And there's such a richness here in terms of what some of the advanced physics, anomalous phenomenon otherwise has. We talked about it more today with regards to propulsion, but certainly on the communication side, your work is very interesting in terms of different forms of communication, and there's a lot of interest. So I know we've done something that I didn't mention throughout the day today, but we have so Diane, we've co-hosted some podcasts with innovators with Diane, with her Ecosystemic Futures podcast with NASA Convergence Aeronautics Solutions. And we've had the opportunity to bring many of the presenters today in, and that's been across fields of pretty much the things that we've seen today: in-space semiconductors, biotechnology, platforms, extended electrodynamics, UAP, advanced communications. Really, so we've got some of these talks. We have an individual speaking for an hour as opposed to a few minutes, and I know you've been part of that as well, Philip. So we'll try to see if there's a way that we can subsequently layer on some of those links or some of that involvement on the recordings of each of the presenters, because you've provided a lot of insight. All right, let's move on to the next presentation.
I still don't have the slides.
Oh, sorry.
I recommend, Anna, that we go to Chassis.
Let's
who
go to
has
Chassis.
their
That's great.
slides. Mhm.
Excellent.
All right. Let's see, let me share my.
Great to see you, Jose.
Nice to see you, Anna. Thanks for inviting. Thanks for organizing this awesome event. Can you see the screen? I guess. Let's see. There. Can you guys see the screen? No.
We see the notes monitor instead of the presentation monitor.
Shoot. Uh-oh. Let me see. How do I switch that? So maybe I'm gonna have to switch. Let me just. Didn't expect that. And let me just remove. Okay, let me try it again. Now, still.
We can see your like your PowerPoint monitor.
Yeah,
It's just not in presentation mode just yet.
it is. Let me see. Yeah, the problem is I have to
Click from beginning. From beginning in the far left top corner.
Yeah. Now the thing is, I do have two monitors, so somehow it switches because in one monitor I can see the full presentation. Let me see. Let me do something.
If you start the presentation and then do the share, that it should be a little bit easier.
Okay, let me do that. Okay, they're going to stop sharing. And okay, yeah, I know what you mean now. Okay, now I can just go to the presentation. Can you see it?
Yep, yeah, we see it now.
Yes. All right. Yes. Okay. Great. Thank you. So again, good morning. My name is Jose Velasco. I am the founder and CEO of Chasqui Inc. We are located in Pasadena, California. And today I'm going to talk to you about the Interplanetary Small Satellite that we are developing with funding from NSF. Thanks, Anna. And we're developing this small sat for fast connectivity, navigation, and positioning. So what is Chasqui all about? We want to deploy the space internet. We want to start with the solar system. It is a bold mission, and we are pursuing it we started with this small sat that we are developing with NSF funding. So the inspiration for this technology is called the omnidirectional optical terminal that you see in this slide. This terminal is, just to give you an idea, it is 8 inches in diameter. It uses lasers for connectivity, and it has it's able to operate at gigabit data rates. It can maintain multiple links simultaneously and can cover the whole space. So hence the name omnidirectional. So we're using this technology as the basis for developing the SpaceWERX. So how do we go from the previous technology? So what we're doing is we don't want to build a terminal that fits a satellite. We're going the other way around. We optimize the terminal, optical terminal, and then we build a satellite around it. So that's one of the novelties that this device has. So in order to do that, in order to provide all these features I just described, first we use the omnidirectional optical terminal I just described, and that's funded by NASA as part of this technology. So this terminal is for short-range connectivity and allow us to connect at short distances with other SpaceWERX in order to create a swarm. So I'll discuss a lot about swarms in this brief presentation. The other thing we added to this terminal is large apertures. We are talking about 4 to 6 inch apertures. So what that allows you to do is allows you to connect at long distances with high data rates. And we're using proven avionics, like avionics that have been flown in other small satellites, like ADCS systems, solar panels, and others. And another two key things that we're using with this new technology, we are using machine learning algorithms, and we are also planning to implement key quantum key distribution for connecting to other SpaceWERX. So as I said before, swarms. The way we want to implement the space internet is using SpaceWERX arranged into swarms, into groups of satellites like shown in this slide. The benefits of a swarm is that you could, the whole system could be autonomous. you could multiply your capabilities. For instance, if one of the satellites can transmit 10 watts of optical power, the 5 satellites transmitted here could transmit at the same time. So the resulting product is that you can get 50 watts of power coming out of the swarm. So going from 10 to 50. So it's a 5-time improvement in capabilities. So it goes as a number. As you increase and add more satellites, you will increase the capability accordingly. So that's why we want to use this satellite in a swarm capability. And we want to make the satellite very modular, affordable, and be able to seamlessly connect with other ones in space as we deploy them. So what are the goals, the next goals for us? We want to implement this network, what we call the Interplanetary Space Internet Network. We call that INSPIRE. And we actually patented this, this technology, this network topology. We got the patent a couple of months ago. And here you see rendering of the INSPIRE network in cislunar space. You can see the groups of satellites, group of spherosats. And those are the satellites that create nodes in space. So any information, say from the moon, that you want to send from the moon to Earth, you could use our relays, our nodes, to bring the information down to Earth. And you can do that multi-gigabit per second. So the speeds are very advanced, very high, and all would be enabled by this spherosat that is being developed with NSF funding. So the next thing we want to do is not only deploy satellites, but also create a network. So you can imagine each satellite to be like a computer. So it uses like a TCP/IP internet protocols, like the typical internet protocols that you have in your computer, to interconnect among themselves and with others. And so basically that's what you have. So you have this TCP/IP, and there is a TCP/IP version developed by NASA. It's called DTN, Delayed Tolerant Networking. And so we want to implement that, which allows encryption. So you will have very secure connectivity in addition to high data rates, in addition to all over ubiquitous coverage. And lastly, I want to show you a picture of our internet, the solar system internet that was patented. As you can see, the goal here is to deploy spherosats along the solar system in the way you see it here. And then, for instance, if there is a mission in Enceladus, Enceladus is a moon of Saturn. If you want to bring the information from Enceladus to Earth, you would use our spherosats that are arranged in nodes to bring the data back to Earth, as shown here. So this is what we are trying to do. And again, we want to thank NSF, Anna, for providing the funding. So we are developing the spherosat with SBIR funding currently. With that, I thank you for your attention. And if you have any questions, please feel free to email me and contact me. Thank you.
Thank you so much, Jose. This is really interesting and compelling work, and we're grateful that you took the time today to share it with us. And obviously, the communications, the security of the communications, the scaling up of this infrastructure, these are very, very important areas. And your solution really has some opportunities in each of these fields. I see Curtis looks like he was about to do something, and then I'm actually going to open this up for, is Anchor on? Is Anchor bot on?
Yeah, I'm here.
Great. Let me present for you.
I'm good. I left that open from earlier comment.
Okay.
Anna, sorry about that.
Okay, great. So let's and just wanted to, so Anchor, take it away.
All right. Rima, do you have my slides?
Oh, I've got them. I wanted to give her a break because we're heading
Oh,
into
okay.
quantum.
Okay, great.
She's our most active interagency colleague in the quantum
Yeah.
in this particular group. So, all right.
All right. So do you want me to share it?
Oh, I've got them. Am I
Oh,
not?
you
I
got
think
them.
I'm sharing them. So I'm on your first one, introducing Javier and quantum propulsion.
Okay, I can't see it yet.
Oh, is it? Does anybody else see it? Curtis, do you see it? I can do it again, hopefully.
Yes, yes.
Yes, we saw it. We
Okay.
were seeing it. Yeah.
Oh, okay. Well, I'll just, that's fine. I'll just
There you go.
use
We're good.
Okay. All right, everyone. My name is Ankur Bhatt. I am the CEO of Hover Incorporated. And a little bit about me. I'm an electrical engineer. I went to UCLA. I got my master's in electrodynamics. And I got interested in propulsion, specifically quantum propulsion, about a decade ago. Just different types of new propulsion, and was kind of curious about it. So fast forward to 2017, I met a guy by the name of Frank Becker. He's also an electrical engineer, and he proposed an idea to me about a potential propulsion system. The reason we met is we were both following a professor named Professor McCulloch, who works on a physical concept called quantized inertia. And we got interested in it, and we wanted to address some of these following problems here. So in current propulsion, it's limited by fuel, which restricts acceleration, range, and maneuverability. And also these problems that you're all well aware of, there's high costs. Obviously, there's environmental damage, using hydrazine, methane, et cetera. And also, in general, when you go into space, there's no atmosphere, so you can't use drones or helicopters or propeller planes, things like that, because you actually have to use Newton's third law. Every action has a reaction, so you have to use a rocket with fuel, carrying fuel, or ion thrusters, pushing things out to move things. So we presented a solution. We're like, hey, is there a way we can create an electric thruster that operates with no propellant and gives you continuous acceleration through just using electrical energy as its power source? Next slide. So we created the hover drive. So our core technology is a reactionless thruster that only uses electrical energy and generates thrust by a vacuum energy gradient without expelling any mass. So I'll try to explain this as simply as I can. The right-hand side is actually the invention. So what we do is we take a capacitor. So for people who don't know, that's just two metal plates. One has a positive voltage, the other one's a negative voltage. And what we did is we took these plates and we got them really close together. And it turns out when you put a voltage there and you have a current, and the electrons can actually build on the bottom plate. And what happens when you get an immense voltage here is the electrons actually get plucked off the cathode, the negative plate, and they hyperaccelerate to the anode, the positive plate. Now we're talking 10 to the 23rd meters per second squared, so immense acceleration. And as far as we know, this has never been done on Earth before. So these immense amount of accelerations, we thought, hey, this might actually give us a new physical effect. The reason we thought this is because physicists like Fulling, Davies, Unruh, Rindler, McCulloch, and also Hawking all propose that when you're that there might be a physical horizon which actually can create a gradient. So this is the vacuum gradient that actually can push an object around. So in 2018, we wrote a technical paper. We matched our theoretical model to our observations, and they did match. Also in 2023, we received the SBIR phase 1. We now have an operational prototype, both a wired and wireless one that's reliable and repeatable as of mid-2024. So the key metrics here are we can go above 2.5 millinewtons, and also our thrust to power ratios are 200 newtons per kilowatt, so immense amount of force per the wattage inputted. So our force formula is proportional to the current divided by the d squared, so that's the distance between the electrode plates squared. So as you can imagine, if we can get this distance very close, we can get immense amount of force, and it could be a total game changer. Now, anytime you have this new type of technology, we need it to be verified, obviously. So we did get a patent in 2021. It also has been verified through DARPA funded research by Professor McCulloch and about, I think, 4 other replications now. We also did independent testings at Hover Labs, and we got ATS Labs to come here and test it on their own. So we're basically at a TRL 4 now. And next slide. So that's the technical stuff. So what does this all mean, right? That was just a bunch of technical stuff that I mentioned, but right away with this type of 2.5 millinewtons of force, we can automatically use this for satellite positioning, which can extend operational life with sustained maneuverability. So having this immense thrust to input power ratio could give you an infinite impulse potentially, and just give you satellite life that can last almost forever. Also, it can be used in asteroid mining. As many other companies have mentioned, this has become a very hot a category of, new type of economy that's going to be created now. So this is $1 trillion market. So our fuelless design enables long-term cost-effective missions that could, mine these asteroids. So this revolutionary propulsion could also be used for, the US national defense as well. So now what's our future vision? So with this, we can do unlimited specific impulse, as I mentioned, limitless propulsion. This can be powered by solar or nuclear power and allow deep space missions, interstellar missions. And the reason this is exciting is when you can accelerate, like when you accelerate on a car, you can keep going faster and faster and faster till you potentially can hit the speed of light. So this is a game changer potentially. And if it's in space, why can't we use it on Earth? So terrestrial vehicles, drones, cars, replace rockets one day, aviation, it's basically a new way to move. So this is a call to action, an invitation to meet people and create strategic partnerships in the future. And that's it.
Thank you for sharing your work and your vision in this space, Anchor. I know that there's a number of people like you that you're really collaborating with to try to develop, these ultra advanced propulsion systems. So really appreciate that you and others are doing the work to advance the state of the art here. And I know everybody's timings can change, but I note that we did have, as we've discussed, many of the fields, and we'll be transitioning into quantum shortly. But I realized that we have one of our colleagues who's previously inside the government, Jay Stratton, who's been on the call, I think, all day, Jay actually was the person who led the UAP task force within the government, highly innovative in his ongoing work in the private sector. And he's very focused on a range of technologies, some of which he might share. And I know you don't have slides today, Jay, but I did want to open it up for you to speak verbally, whether on your former experience or some of the areas of technology that are of interest. And obviously you've had tremendous depth of experience with anomalous phenomena and advanced physics. Can you hear me, Jay?
I can hear you.
Great to have you. Thank you so much for making the time.
Oh, no, I appreciate it. I didn't really prepare anything. I've just been listening all day long.
It's just your whole career has prepared you for.
I guess so. No, it's a pleasure to be here, and the previous events that you set up, Anna, it's been awesome. As she said, and I've got my colleague and longtime friend Hal Putoff on here as well. Starting back in the early 2000s, we saw the need, my colleague and I at the Defense Intelligence Agency, to start paying very close attention to this topic, advanced technologies, emerging technologies, and really kind of the areas that, the stigma has led for us to ignore for many years. So, we created a program that Hal referred to as OSAP, to address those issues. And that really started around 2005 and resulted in.
Jay, just as a reminder, some folks might be listening to this out of sequence. So OSAP and the UAP task force, can you just give kind of the minute on that? What it was?
So the DIA program, which you jumped in earlier and said the DoD or the DoD's program, and really it's the intelligence community's program. DIA is part of the IC. The D in there being defense predominantly means the DIA looks at foreign defense capabilities. And we were looking at this from, and I hate to say it now, but a threat perspective. and the reason I say I hate to say it is because threat is capability plus intent, and some of these things we just don't have an idea on the intent. So determining threat, maybe it's an emerging technologies threat or a concern. Anytime it can potentially exceed our own capabilities. But that DIA program focused on that and a contract from 2008 to 2010. And then we transitioned and tried to move the program to a couple of other places. Fast forward to 2015. I created a program called ATIP, which was a derivative of OSAP, and actually ATIP was a nickname for OSAP, and I know there's a lot of crazy names, but Advanced Aerospace Threat Identification Program. But those 2015 events were the ones that you see now in the news: the gimbal, the go fast, Ryan Graves, who usually participates in this. His wife is having a baby currently, so he's not here. But all of those events started to happen.
Reason to miss a meeting. We love that. Very excited for the family.
And those events help fuel, further highlight that need on the U.S. government side that we got to do something about this, which led to the creation of the UAP task force in 2018 into 2019 as when I started building it. I spent over 2 years building it out before the public even knew about it in 2020 when DoD established it. And at that point, it was truly a whole government interagency effort, kind of the dream of my 15 years plus at that point of looking at this topic and knowing everything that we needed with all the different authorities. And that led into where we're at today with ARROW, the All-Domain Anomaly Resolution Office under DoD. And I think, a few hiccups here and there, but I think now Dr. John Kozlowski, who has ARROW, is approaching this problem set and dealing with the topic appropriately. And I hope that, I'll say my legacy or the legacy of all of those involved carries on and that the government continues to take it seriously and that we never have to look a pilot in the eyes again and say, sorry, can't help you, or the ridicule factor and all these other issues that happen from that. So, that's kind of the cliff notes of the history. But the UAP task force recently got an award from the DNI. It's the first UFO program to get an award at that level, to my knowledge. And I'm really proud of where we're at today, and that we can have events like these to discuss this topic seriously, and everybody that's involved and putting their brains on this problem.
Thank you so much, Jay. Thank you for your long-term work in this space, and we definitely, and your leadership and bringing people, during your service to the country, across the interagency together on this. And what we see is that there's tremendous engagement, so we see many colleagues, as you can say from your time, high levels of engagement and interest. We see that on the open and discussable, and then the non-classified side, we see high levels of interest and engagement, openness. We see entrepreneurs and researchers, as we can see throughout. These are the areas where people have seemed, by virtue of how many people participate and stay on and provide ideas and questions. We see that science. We went back to some of the innovators when we were talking about this earlier. We kind of were saying, and so we were expecting to get more mixed feedback, to be honest. And what we found was that out of a large group of entrepreneurs, there were some that were saying, well, we're scientists, we're engineers, we got to figure out what's out there. We gotta figure out what this is. And then we had somebody else on the call who said, this is the thing, and this is all in pilots' face all day, every day. And so, the questions are kind of, what do we build from this, or what do we do? So, just to see that engagement, and while in the past, and in some cases there can still be some level of stigma that has been, much of it has been really eliminated, and there's ability to discuss seriously. We find that disruptive innovators really across all fields of technology face extraordinary headwinds. So it's kind of interesting in that innovators who are disruptive in their approaches, if they come with, we say something that you use it every day, something as basic and mundane as, you know, a battery, and they come up with a higher performing battery, the experts will say, no, we don't think that's going to work. So this pushback on things that are different is certainly not constrained to the field of UAPs. It's really all areas of disruptive innovation. But the silver lining of that is the people who push disruptive innovation are used to working through, you know, kind of these areas where they've got to build out what something is and what the future looks like. So they're very comfortable in those spaces on the innovator side, from what we've seen. So you've contributed a lot to that, obviously, with your long-term work and that of your colleagues.
I appreciate it. I'm proud of where we're at today.
Giving the visibility. So was there anything that I don't want to, I want to be respectful of your time, but so one of the things that we didn't really have enough time to go into with Hal is there's so many of these areas of technology that really have that intersection with anomalous phenomena and UAP. And, you know, over the course of the day, we've said advanced propulsion, advanced materials, communications, cloaking, space-time metric engineering, biological effects. There's so many of these spaces, but, you know, obviously you've been involved in, you know, the publicly visible information, you know, on some of that and the DIRD documents and otherwise. Is there anything that you would share with us with regards to the convergence across sectors or specific areas where you think that these UAP and anomalous phenomena insights are very important?
Well, I don't think we should overlook, and you had, you know, Paul and others talk about remote viewing and that consciousness connection. I keenly believe that consciousness is a key aspect of all of this, and perception and all the things that come from that. And that's an area that can get confusing, right? If you look at all of these recent drones day to day, right, it's honestly driving me crazy because people are throwing in, you know, video of a Cessna citation on final approach and calling it a UAP. You know, it's definitely a Cessna citation. And then folks start throwing around the terms mimicry and other things that we've definitely looked at. And it gets like to Skinwalker Ranch, as you know, I'm involved out there. You know, the things that you see, and are you really, you know, how is your brain forming that thing you're seeing, and can that be manipulated? And I think that technology is an area that, you know, I certainly focused on with my friends Hal and others to try to understand it, and that consciousness connection could be a key to understanding how some of these UAP are flying. You know, how they're acting, how they're controlled, I guess is the best way to put it, right? So you got to have that kind of open-mindedness to approach this topic, and I hope that my government, you know, folks are open to those kinds of things. And I know that there are still some key players that are open and thinking out of the box about all those kinds of things. So, I mean, I think consciousness is the area that I would want to put more resources and time into if I were still there.
And it's interesting because there's quite a bit of access to consciousness, you know, on a personal level type experimentation. So it is interesting in that, you know, to get into UAPs, I mean, maybe you've seen one or more, maybe you haven't, but if you haven't, you're kind of digging through other people's data. Whereas some of these consciousness or the remote viewing, it really just takes a couple people and a sheet of paper. So you can kind of step away pretty quickly from the, do I believe the reports, you know, or somebody else's, versus you can get to that primary experimentation at the cost of a sheet of paper, a pencil, and 15 minutes or more of somebody's time, you know, at the most basic level. I mean, obviously there's extensive training to build the high-end capabilities, but some of that initial testing is pretty immediate. So thank you for bringing up that consciousness work.
I was going to say, it took me years to move away from that nuts and bolts mentality of, you know, as an aerospace engineer, this is how it flies, thrust, you know, power, et cetera, you know, to there's a lot more to this, right? Hence the name, you know, unidentified anomalous phenomena or aerial phenomena, however you want to look at it. That phenomena word is key in the definition and understanding of all of this.
And then I guess there's many of us on the business side that say, okay, you know, mechanism second, you know, and outcomes first. And so what's interesting about some of these spaces back to, if you see something that's operational, that's a high performing propulsion or comms or whatever it is, you say, well, we better pay attention to that. Or how do you do that? And there's many fields of science. I mean, my PhD was in nanotechnology, and there were things, 15 years ago that you'd say, okay, nanotechnology does this, and you weren't really sure why, it behaved that way, but you could use it for things from a pragmatic standpoint. So I see Lou DiCero in the chat. Lou, you've made a couple great comments today that I haven't really read because they're in the chat. But Lou, do you have capability to say anything, or are you in the background? Thank you, Jay. Great to see you. Is Lou still on? Okay. I know we've got presenter permissions for some, and then we've got also esteemed colleagues that are a bit on the other side right now. And we're going to be rolling in pretty quickly to the quantum work. But so Lou's mic is not working. Okay. And I don't know, Larry might be able to help layer on some of those insights as well, because I know, Larry, did you have anything that you wanted to share from some of the comms Lou's been sharing? Larry might be on mute as well.
Yep.
Oh, here we go.
I'm up.
So yeah,
Yeah,
intersection, EED, UAP, your own thoughts, and then anything that Lou's raised that's shareable.
Yeah, Lou's work has been first, he brought EED, extended electrodynamics, to my attention a few years ago. And as a consequence now, with some NASA funding, we had him implore and modify density functional theory codes, as I mentioned before. But it goes further than that. Lou has done a great deal of work looking at the intersection of EED and general relativity, along with work that's been published by Thomson Brown, as well as some of the Russian work that has been, I think, partially replicated by a number of people talking today. And the fundamental thing comes down to a meeting that was held in the Senate back in November of 2023, where they requested a briefing on low energy nuclear reactions or lattice confinement fusion, extended electrodynamics, and UAP, the conjecture being that the first provides the power source and the second one, EED, provides the propulsion means. So that has carried on, and several of us are examining ways to prove the existence of this. Hal probably doing much of the heavy lifting over the last 25 years with those patents that he issued. All of these are predicated on a similar quantum mechanical effect, that you can propagate what's called a potential without actually having an electromagnetic field that carries that through. And the potential results in your ability to generate and or measure a phase difference, and that is the an example of a quantum mechanical phenomena that does not exist classically, is not covered at all in the original Maxwell's equations as reformulated by Heaviside, but is not only been acknowledged since the 1950s, but is now apparently beginning to be deployed by people here.
Thank you, Larry. And I think that Lou DiCero's mic has been opened up, which is very interesting, because Lou, along with, I mean, obviously we've spoken to a number of the other experts in EED earlier today, extended electrodynamics, but Lou has also been one of the leaders in EED alongside Lee Hively as well, who I think is not on the line today, working separately. But Lou, I think we've got you on.
Yes, I hope you can hear me.
I can, thank you.
Okay, very good, thank you. Yes, to give proper credit where it was due, where it's due, we were first notified by one of the staff members of the United States Senate Armed Services Committee, who shared with us a key paper by a Russian theoretician by the name of Vyacheslav Dyatlov, which can be Googled fairly simply, and Professor Dyatlov has published a fairly lengthy paper on the coupled Maxwell Heaviside equations. So the standard Maxwell equations may be, according to Dyatlov, only a small part of a larger group of coupled equations. There is another set of almost identical equations coupling spin phenomena and gravity, just like the Maxwell equations couple electric fields and magnetic fields. So the Heaviside equations couple spin fields with gravity fields, and they in turn are coupled to the Maxwell equations, which explains why Townsend Brown was able to apply a very large electric field to an asymmetrical capacitor and actually generate usable quantities of thrust force without having to expend fuel other than to generate the electricity. And so we're very excited about the possibility of propellantless propulsion using that principle. And it's also a very nice way to, shall we say, provide a nice load for nuclear reactors and what have you that may have the capability of generating many tens or hundreds of megawatts or even gigawatts, and to use that to generate high levels of thrust for deep space vehicles.
That could certainly provide the game changers for travel far deeper out, far faster. Many of these things that we're talking about here. So I appreciate you bringing that up, Lo. Did you want to cite any? It's okay if not, any agencies that have been particularly active in the work.
Well, I am not plugged into any of the unacknowledged special access programs, but I wouldn't be surprised if there are pockets here and there, perhaps out in Area 51, where that kind of work is being pursued. Certainly, it's something that our Navy colleagues have some interest in.
So, and you work with Navy, so I guess you say Navy colleagues. That's kind of. I wasn't asking about Area 51 per se, but thank you. Okay. So next up, let's get into. I think we have Brian's slides. Rima, do you have Brian's slides? Do we have Brian on? Yep.
I think
it looks like we do have Brian on. Brian,
Yeah.
do you have your own slides available for projecting, or did you need us to pull those up? Brian, can
Rima,
you
I'll
hear
send
us?
you. Rima, I'll send
Brian, no, I talked to Brian. You need to have him. You need to put the slides up for him.
Rima,
Okay,
I
but
will send you the
can we
link.
get audio from Brian?
Is he? I don't know why
His mic is blocked. I don't know if he blocked it, or Diane, if you need to unblock it.
No, he can unmute it. We can't manually unmute, but he has the ability to.
Okay, I'll call Brian and ask him to unmute it.
Okay. All right. Well, we're going to be, while we're waiting, I think this is a great time. And there's definitely overlap between some of this EED and some of this phenomena with the quantum.
Brian, you need to unmute your mic.
Okay. And while we're waiting for him to do that, and why don't we, I think this would be a great opportunity to listen to Rima share with us some of her thoughts. She's a leader over at DOE who's very active in quantum and also building out some space opportunities with DOE. Rima, would this be a good time for you to share some of your thoughts?
Sure. I was just gonna kind of kick it off with, let's see here. Can you guys see my slide?
Yes.
Slideshow. There we go. So just want to kick it off with why quantum is so important. And I think it's been sprinkled out throughout the day, right, with a lot of the topics that have been covered. But from a DOE perspective, you know, we're really interested in protecting against a quantum threat and a quantum computing that can hack all of our security, specifically around quantum random number generators being sort of taking things to the next level, because our RSA tokens today are based on classical algorithms. And then so that really kind of started a lot of interagency work that opened up a lot more interest in quantum. And the DOE has been investing in quantum for some time, but the QIS centers, which are the Quantum Information Science Centers initiated by the National Quantum Initiative Act, really created a huge opportunity for us to deploy over $625 million across 5 centers to stand up these capabilities at the national level. But what's also interesting is quantum activity has been taking place for quite some time, and we've got projects that with the utilities that have been around for like 10 years. EPB is based out of Chattanooga, and there's a collaboration with Oak Ridge National Lab that has just been reinvigorated and has been getting a lot more support. And we've moved away from basic science research and have started investing in the applied space. So we actually invested some of the grid modernization initiative funding mentioned here in the middle. A portion of the 39 million went to stand up basically a sandbox for developing quantum capabilities at the national labs in collaboration with industry that can be deployed directly within the energy sector, because we see that as a very interesting use case that can help bring scale. And then, as Anna has mentioned throughout earlier in the day, that there are loan guarantees out there that are in the billions of dollars, and DOE has one of those as well. And I wanted to highlight that a quantum company, LongPath, is a great example of a quantum sensing, quantum laser technology used for methane leak detection that was awarded a $189 million loan guarantee to scale. So here's just a quick snapshot, of some capabilities that we have that are both terrestrial and space-based. What's interesting here is that a lot of this quantum technology, like quantum sensing, which we're going to highlight today in particular, the same sensor could become rugged enough and durable to be able to withstand space and be able to provide the same capabilities in space as on Earth, or different capabilities. So one sensor can do multiple things. And so we're really interested in highlighting the capabilities around position navigation, timing, mineral prospecting, and resource exploration on Earth as well as in space, looking for water, ensuring that our infrastructure is behaving properly, like I mentioned, leakage detection, finding caverns where we can store CO2 on Earth, or find caverns in space for opportunities where we can actually maybe allow for colonies to exist, for example, or manufacturing centers of space. So very much in line with a lot of the conversation today, and some of these quantum technologies are being developed, within industry, and a lot of collaboration has been taking place with the DOE and with the national labs and with many of our agency sisters and brothers as well. And remote imaging from space gives us other capabilities. And from a DOE perspective, if the more that capable that we are in being able to identify things like fires in remote areas before it hits our actual critical infrastructure like the grid, then the better off we will be and be able to protect our populations on ground. So lots of great opportunities here to develop quantum technologies in space, but also in space for Earth. And we see this as an opportunity where we can support a quantum-enabled space economy for the revitalization of Earth, as well as obviously for exploring space. So with that, I want to jump, if we can.
We really, as your interagency colleagues, I mean, so many of the agencies have an opportunity to play an important role, and many a number of them were present today in the attendees. There's also many more that we collaborate with and work with on an ongoing basis. But clearly, when we think about infrastructure scale, I mean, just the opportunities, some of these resources off planet, just the potential of what
but I don't care about a
brings
camera.
to the table is very helpful. So we hear you now. So now we hear you. Now maybe when you don't want us
Oh,
to
I
hear
gotta
you,
turn
we
the
can hear you.
volume up now.
But yes, so we hear
Okay,
you
I can hear
perfectly.
now.
Yep, we hear you. Maybe Larry can tell Brian that. All right.
Yep. Brian should be on now. He doesn't have
Yeah,
camera.
I hear you all. I hear all of you.
Okay, great. So are you flipping your slides or do we need to flip them? Who has them?
No,
Well, I didn't.
let
prepare.
Rima run the slides.
I have them.
You have them? Okay, great.
Yep.
Excellent.
There we go.
Is this an okay way to project it?
No, this is the wrong set of slides. There's a more recent version, Brian Ahern V2.
I mean, if that's fast, but otherwise, kind of V1's okay too.
Have a feedback loop. Yeah, that's what I have right now.
Larry,
Rima, did you find version
do
Brian Ahern V2? Because I sent it to everybody.
Oh, you sent it? Do you mind if we maybe get started with the quantum folks while I try to pull up Brian's slide?
Sure.
Fine by me.
All right, let's do this then. And I will multitask.
Or Larry, why wouldn't you just present Brian's slides? Do you have it open? It sounds like you're the one who sent it to us.
I can open it up, yes.
Yeah, why don't we just do that? I don't know how long it takes you.
Yeah, it just take me a moment here.
And Lou, you had a comment in the chat that Hal has also brought up publicly. So if you wanted to share that verbally, you can while we wait to get this slide up.
Okay, sure. Yes, Hal demonstrated a really a fabulous pure quantum sensor in the Josephson junction experiment that he performed in conjunction with that radio transmitter. So he took the transmitter and an antenna, surrounded it first with a Faraday cage to kill off the electric field, and then a mu metal shield to kill off the magnetic field. So there should have been no fields of any kind being emitted outside that double shield. And yet the vector potential waves from Hal's transmitter went right through the shielding and into his Josephson junction in the next room, suggesting an excellent opportunity for new kinds of wave propagation, and perhaps an interesting opportunity to listen in on everything that Uncle Vladimir is telling his GRU agents.
Larry, you've got your hand up?
Yep, I've got him up on it. I need to have access. Oh, just what happened here?
I found it. I finally got it. I found your thing.
Oh, okay. All right, great. So let her put it up.
I just need to. Where is it opening?
So Lou, thank you for making that bridge between quantum sensing and some of these other fields and forces.
There we are.
Thank you, Rima. All right, so we've got Brian's presentation up.
I don't see anything.
We've got your slide, invisible energy input from neutrino magnon interactions.
Well, all my screen says is Zoom.
I think that's how you've got your screen set up. Rima is presenting it. So maybe
Okay, Anna, I can read what's on the slide, and Brian, you can tell them what's on it. It's the slide with the car. It's the first one. The title reads Invisible Energy Input from Neutrino Magnon Interactions, Dr. Brian Ahern, with partial funding from EPRI. And the comment in there is Arthur Manelis converted this gas-powered car to electric with a 57 horsepower motor using 1,000 pounds of lead-acid batteries, then replaced it with 350 pounds of Thunder Sky brand lithium-ion batteries. All yours, Brian.
Oh, okay. Well, Arthur Manelis from Pelham, New Hampshire, was looking for a way to make more power out and in over unity device. And they often look for magnets. And with strong magnets, there's a lot of tricks you can pull. So they asked me to put a team together to evaluate Arthur's car, which was going further than it should have on a battery. The power supply that he built is in the trunk of his car, and it ran for 2 weeks at 60 watts. 60 watts of a LED lamp. That would be enough to cancel the battery by a factor of 4. And at the beginning of the test, it was at 165 volts. And at the end of the test, it was 165 volts after having just run for 2 weeks at 60 watts. That's the bottom line. It's an unbelievable amount of energy, and you can't figure out where it's coming from. But we had enough data to suggest that it had to have had the same properties as a neutrino. And neutrinos are a highly magnetic system, and with the onslaught of magnon technology, it looks like you can form a magnon neutrino interaction, and that's where the energy came from. It's just like a solar cell, except you have an intermediate play with neutrino and magnons. So we're just learning, well, why is this not well known? Because after we did those testing, Arthur did some more tests, and he burnt out the device completely. It was a lithium ion fire. And it was lucky that we were doing this testing on his front lawn. So that ruined it. And for 2 months, 3 months, he tried to rebuild it, and he died abruptly. So what we had was just a bag of parts, no schematic diagrams to go on. And it wasn't until recently where we found his latest notes that he said he agreed that it had to come from outside the vehicle. It had nothing to do with the vehicle. It was just a battery. This is charging a battery. The current has nothing. There's nothing to do with automobiles. And he suggested that we try running magnets in their bucking mode. And that seemed to make all the difference in the world. Nobody had ever done it. Use bucking mode multiple times in the. Excuse me for my speech is not as best as it could be.
Brian, do you want to switch to the next slide?
Oh, I thought you were running the slides. Okay, go ahead, the slide.
Next slide.
What is it?
It's the
This
image.
shows the yeah, I'll read what it says on there. Can you raise that up so I can't read the text? Yeah, the ferromagnetic billet's magnon excitation was converted to power with this circuitry. I can't read the rest because, hang on. The voltage rose smoothly over 7 days, going up 10 volts, 28 watts produced, but how? And Brian, they've got the picture of the converter in there right now.
Power supply is in the trunk of the car in a wheel well, and it takes energy from the battery and it puts back more energy than it took out. Sounds like it's a violation, but it's not. Solar cells would do the same thing. If I had just put a solar cell there, you could take energy from photons and drive a device, or you can just let it build up a voltage. It's the same thing, except instead of having a photon causing the action, it's a interaction of neutrinos with magnons. You create the magnons with that power supply, and the neutrinos are everywhere. So wherever you create the magnons at a sufficient concentration, you'll get energy made in the form of electrons going to your wiring. And that's what we saw.
Rima, go to the last slide, please. So Brian, I'll read what's on the last slide, which is showing the light on in the front of this car. And what is written on the slide is, I suspect that the ferromagnetic billet used was interacting with the ever-present high-density solar and astrophysical neutrino flux.
Entered a neutrino era. It's going to be incredible. It doesn't have any exhaust. It looks like it has no intake because it's invisible and it goes right through us all. But with the right magnetic conditions, you can do it. And there's no limit to it. It will be the only form of energy research to come for a long time. The size of our billet in that power supply is where the energy came from. If we compared that 60-watt output to what a solar cell would be like, it's 50 times more energy dense than solar cells. It works at night. It works on rainy days. Nothing impedes its motion, its mechanism. So it really is a neutrino era. And it's just coming. We're just learning how to.
Brian, this is something that, in terms of, if something like this is reproducible, this is a really, really big share. So thank you for sharing it with this broad audience. Much appreciated.
Thank you. I appreciate you staying with me.
Thank you. All right. So these are high bars to follow. Wow. But then we have a tremendous set of presenters in the quantum space who are getting started. And I think we have, let's see, we're doing well with regards to anticipated timing, because we have, trying to see, Rima, we have, I think, 3 presenters in quantum: SB, Quantum, Cubatech, and Inflection. Are you expecting anybody else in the group?
And Mesa at some point. So
did they get us their slides? So that's great.
Yes, yeah. So I got them this morning. So why don't we start with Inflection, because I think they've been waiting the longest. So just thoughtful people. I asked folks to start on time because we're ahead of schedule. Now we're on schedule, sort of. So why don't we just Max? Did you want to go ahead and start?
Yeah, I'd be happy to. Hopefully Jack will throw up the timer for me so I don't go over time. I'm Max Perez from Inflection. I'm the VP of Strategic Initiatives and the acting unit lead for our timing products. I'm going to talk about 3 different technologies that we build here at Inflection for the space ecosystem. Primarily, we're based in Boulder, Colorado, but we also have facilities in Madison, Wisconsin, Chicago, Illinois, Oxford in the UK, as well as Australia. The first technology I'm going to talk to you about is our ticker optical clocks. This is a next generation optical clock technology. It's a quantum technology. It's designed primarily for the high performance time and frequency market. To replace hydrogen masers. The generation 1 is a rack mounted system that is designed for ground applications. For the space ecosystem, this is used for radio astronomy. This is kind of the backbone of the Very Long Baseline Array in New Mexico, as well as the Deep Space Network around the world, and tracking stations all across the world. Our second generation unit is supported by Space Force to space qualify these clocks for the resilient GPS and other next generation GPS and GNSS systems. and provide a path to upgrade to Galileo quality on much smaller platforms. And the third generation is a photonically integrated version that will allow us to access to the high volume and lower cost markets in LEO deployed applications. You can go to the next slide. We also have a very long history deploying things to the International Space Station. We were a part of the Cold Atom Laboratory, which demonstrated cold atoms in space for the first time. As a part of an upgrade, we were able to demonstrate gravimetry experiments on the Cold Atom Lab. And based on that work, we were invited to participate in the QGG, or Quantum Gravity Gradiometer program, which allows us to do Earth monitoring using gravity systems. This allows you to monitor resources like water resources, the changes in ice caps, as well as doing a resource location underground using gravitational gradient information from space. And we're very excited to be a part of that ongoing program. Next slide. The last technology I'll talk to you about is our Skywire quantum RF technology. This is an emerging technology that allows you to use a single aperture in order to map and monitor the spectrum from waves all the way down in the kilohertz up to the terahertz using a single system. This is essentially a laser-defined passive antenna system. So it's very suitable for ISR and other passive electronic warfare applications. But because it is a very compact aperture and it's highly tunable, replaces bands all the way from the HF up to the K band and beyond. It's suitable for compact space applications for things that you might think a Hawkeye 360, for example, being a part of. I guess with that, I'll close, and thank you very much.
Thank you, Max. Really appreciate it. I think we're at time, right, Anna? I don't see.
Yeah, this is perfect. And I just want to thank you so much. And also, Rima, if you have comments on, you really brought forth many of these leading quantum researchers and companies. So please feel welcome to weigh in at any time.
Yeah, no, I think that the work that you're going to see from these companies today have many dual purposes, multi uses. Again, the same sensor just applied in different use cases, which is really exciting. Why don't we go to Qubitekk next, because they were supposed, I was going to have them go first originally. Corey, do you want to introduce yourself and take it away? I saw you were online.
I am. Thank you. Appreciate the opportunity. Hello, everybody. I'm Corey McClellan. I'm the Chief Revenue Officer at Qubitekk. We're a quantum networking company. It was just announced at the end of November that IonQ, an ion trap quantum computing company, is purchasing us. So that is in process at this point. But I want to talk to you a little bit about our technologies and what we've done. As people may know, that quantum technologies have the possibility of dominating the world as far as integrating with strong AI and quantum networks, quantum computers. So whoever wins that race will dominate the world economically and from a national defense perspective. So we're very energetic in trying to get our products to a point where they're commercially viable in relationship to quantum computers as well. So we use quantum entanglement to secure communications via fiber and free space channels. And if you want to go to the next slide, we've applied this in a couple of different ways. One is working with a company called Zeros in quantum time transfer and alternate PNT architectures. And this is something that we will be able to demo here in the March timeframe on a terrestrial basis, just to show that it works. We're shooting to try to get on a bird here in the not too distant future. This is work that started with the Air Force. We had a quantum entanglement on drones program that is being expanded now. And then this takes it to the next level to satellites. And this also includes quantum time transfer as a possible GPS alternative or replacement in the future. And then next slide. And a little bit about how we got here. We installed the first commercial quantum network in the United States at EPB in Chattanooga, Tennessee. That quantum network has been up and running for the last year and a half. Had multiple companies, and Oak Ridge National Lab have come down and done some testing on the network. It's basically a quantum entanglement distribution network that's available for you to come in and plug in your equipment and test it and see how it works. And from a technology maturing perspective, basically the bottom line of this pyramid is basically where we are at EPB. And that as new technologies are developed, including quantum repeaters and quantum memory, then we'll be able to expand that network and the distance of the network as well. At some point, EPB wants to be a node on the quantum-enabled internet of the future. That's a real quick rundown of where we are and what we've been doing.
Thanks, Corey. And so I just wanted to mention that, you know, when it comes to quantum, or if we just talk about GPS for a moment, and the value of GPS for our economy and how everything is so dependent on position, navigation, and timing on Earth, but then obviously the same will be true in space. We know that on Earth, if GPS were to go down, it would cost the US economy $1 billion a day. That's how much loss we're talking about. So ensuring that we have very resilient timing capability and securing our communication is incredibly important, because we're just talking about GPS for $1 billion. Imagine now the communication networks if they were compromised. So in addition to the value that it creates, it also shields us from losses. So very significant and important for our economy.
I just want to double down on what you're saying, and I really appreciate you bringing up just how important and high value and critical to security and resilience this all is.
Yeah. Next up, if I can call on David Roy-Guy with SB Quantum.
Hi, everyone. David Roy-Guy. I'm the CEO and founder of SB Quantum, and we're building quantum analytics for Earth and space. We're based in near Montreal in Canada. We're a 23 people team developing diamond-based micrometers primarily for now. Here you have a picture of our team delivering our first sensor at the end of last year. Our flagship project in the space domain is really the MACWEST challenge, sponsored by the National Geospatial Intelligence Agency. And that mission is about having independent network of low orbit satellites to build the world magnetic model. So the launch, we're in the final phases of that program. The launch is planned for the end of 2025, and we're working with Spire, US, and Glasgow in order to fit our diamond magnetometer technology to provide very accurate measurements of the Earth's magnetic field. In parallel, we're also planning for the future. We're mandated by ESA to look at the potential of a quantum diamond magnetometers for Earth observation missions. We're currently in the sensor specs definition, and we're looking in the second quarter of next year to proceed to sensor building. Next slide. So we spent the last few years through the MACWEST program qualifying our diamond magnetometer technology. It's now at the state where it can operate in low Earth orbit conditions. So it's been successfully tested for radiations in TVAC, for vibrations for a SpaceX launch, and also magnetically qualified at the NASA GSFC and also facilities in Canada. So at this point, we just broke through the 1 nanotesla per square root of Earth's sensitive vectorial, so that we can measure the orientation of Earth's magnetic field with a high level of accuracy, so around 1 nanotesla over extended periods of time. Next slide. So yeah, some of the I thought you would be interested in some of the technology advantages. So when we compare to atomic vapor magnetometers, which are total field magnetometers, basically the NV center magnetometer advantage is to provide the vector measurement in a very small volume and based on quantum, so thereby reducing drift. But there's also side advantages, like there's no dead heading error or dead zones for this sensor. And the tolerance to vibrations and radiation, as I just mentioned, is a key aspect when we compare to AVMs, atomic vapor magnetometers, because it's a non-resonant excitation. So for now, we stuck with the commercial off-the-shelf components, and already we have something that is pretty compact, that is handheld. So I have one right here with me if you look at my screen. So it consumes 4 watts. Actually, Rima could see a live demo at IEEE Quantum, detecting some magnetic rocks. So that was great. And a big aspect of what we're developing is also compensating for the platform magnetic field noise. So we've pioneered ML compensation algorithms for a CubeSat platform and are currently adapting them for drones, so submarine drones and also air drones. So yeah, we're looking for new opportunities for missions in Earth magnetic field observation, possibly connecting also to the magnetic navigation domain. So feel free to reach out, David at sbquantum.com. Thanks.
So this is incredibly fascinating work because we're talking about a handheld quantum sensor that can do position navigation timing. It can do mineral exploration, and it could see through walls. Like, it's just fascinating.
Yeah.
And that tech is here today, coming out of a pink diamond. Love it.
Thank you for sharing this with us.
Thanks for having me.
All right, so last up, I think we have Mesa. Do we have, and I know that we got last minute. Okay, great. I know you're traveling.
I am here.
Let me pull up your slide because I think I had to pull it up separate. Yep. There it is.
All right, now I'll go ahead and start to introduce myself as we get the slides up here. Again, Wale Lawal, I'm the CTO of Mesa Quantum. We're a early stage company at this point, focused on the timing element of PNT, really trying to bring a new tech refresh to technology that was really demonstrated out of CU Boulder NIST, which is where we're located and where we're spinning out of. The chip-scale atomic clocks are essentially miniaturized demonstrations of what we currently have in our GPS satellites. They've worked decently well for the last decade or so, mostly aiding in military GPS denied environments where you need some type of holdover on your timing signal. However, there's been like an increasing need for alternatives to GPS for geopolitical reasons, as well as just for improved precision timing benefits. And so we decided to, similar to what Inflection has proposed, but on a different scale, really advance the broader adoption of these atomic clocks to mass market opportunities, making them, demonstrating some new improvements into them, making them even smaller than the existing CSACs, and really, really driving new improvements in the manufacturing and reliability side, so that we can actually produce these at scale and at a volume that you can start to see them integrated into not just DoD, but into autonomous vehicles, into our energy grid systems, into telecommunications, into LEOSat operations, and some local PNT applications like GPS warehouses, satellites, or construction projects. And so this is an exciting a time to really drive new improvements in the timing domain. And so you can kind of see our timeline. We're looking for our first full product demonstration Q2 of 2026, where we would have production scale CSACs with near form factor, better precision, but then we would be quickly moving towards some of the IP that we're currently developing to ultimately within the next, I would say 3 years or so, have these size for mass market opportunity, chip scale atomic clocks, with we're talking microsecond level precision, above and beyond 24 hours. And in some cases, really trying to push demonstrations closer to multiple days, as opposed to what's currently available with the existing CSACs, which just barely hit a microsecond within the 24-hour period. So that's kind of our goal and our target. If you hit to the next slide, really, this mission was kind of driven by what we noticed in the existing CSACs, that they were still, although they're called chip scale atomic clocks, they're still about the size of a golf ball. They can still range from $3,000, $10,000 per chip. So if you're talking, different, devices that need to integrate this type of timing, you're very limited in your market based on that cost. And then you still just have some reliability issues with many customers that we talk to. And so, some of the things that we're doing, just wanted to highlight maybe one. There's several different efforts that we have pursued, but one is just, starting to integrate novel materials, nanophotonic materials, that, can replace certain components that are required to be epoxied together and, are not very manufacturable as you try to produce these at scale. And so we've been able to demonstrate some of these improvements in the material that wasn't available in the last decade. These are, much newer nanophotonic materials that have become more relevant in the last 2 to 3 years, I would say, from a demonstrated commercialization perspective. And so we're implementing new components at that level, but then we're also really bringing a lot of new in-house design IP to the table with the outside fab. That's a core benefit to what we bring, as opposed to some of the existing players in the space who have internal fabrication. And so they're very limited in their design capabilities, versus we can do rapid prototyping for both niche and mass markets to really drive precision timing. And so those are some of our strengths. If we go to the last slide, maybe. I think the screen may have went away from the full screen share. One of the areas that we just wanted to emphasize with these miniaturized, low size, weight, and power atomic clocks is the ability to contribute towards, assured and resilient PNT. That's been a big push. So as you're trying to leverage timing signals, or PNT signals in general, from Wi-Fi, from cell towers, from our energy, even our energy grid, system, and LEO satellites, which are much more compact and require much lower size precision timers. These type of clocks can play a crucial role in really advancing our assured resilient PNT. And then just some of these other architectures in space, when we talk about PNT solutions, as we think about the early demonstrations of timing on the Moon and Mars, really having these maybe ground-based timing systems that use these, that are much easier to transport, in the SpaceX ship, as opposed to big satellites that you would need to relaunch. These are opportunities to demonstrate some early timing signals, ground-based, with these miniaturized precision times. So we're excited to kind of pursue this mission of mass manufacture with broader adopted chip scale atomic clocks, and happy to talk more about this if folks have any questions.
Thank you so much. Rima, what a tremendous group of quantum companies. Would you like to add anything more on this one?
I think that this is just laying the foundation for the future infrastructure that we will need in space to support all the activities and the manufacturing and the exploration that's been discussed today. So, these are the early creators that are really leaning in and ready to take off. But also kudos to you, Anna, for putting this together today, because the discussions earlier today also identified materials and components that I think some of these quantum companies are going to want to consider in developing their devices. Like some of the diamond manufacturing in space might be better suited for quantum sensing than maybe the terrestrial diamonds that some of these.
Yeah, I was about to say, Rima, what you're doing here is
closing the loop.
identifying the solutions and some of the actual, I mean, the application areas and some of the solutions for manufacturing those we started to identify this morning. So those two will merge as we go forward into the future, I believe.
Right.
I did just want to, as we're closing out for the day, I mean, we're just, in gratitude for everybody's time. I mean, so many extraordinary presenters, and this is something that, I mean, many of the interagency colleagues that you've seen visibly and many, many more who weren't visibly presenting today. I mean, it's really a case of engaging with entrepreneurs and innovators all the time, kind of the all day, every day, listening to them. And they bring us, they bring us the most exciting and amazing data, progress, solutions, concepts, ideas, visions. And we're not just listening, we're here trying to help you build, find resources, try to find paths forward. And it's just extraordinary what people are doing. And I want to give the other colleagues who have been a part of that an opportunity to just add their few sentences as we close out to the extent they want to. I know a lot are, I've seen some balloons going up with Larry, and he's
Not mine.
Did you have a question, or did you want to help us close out?
Actually, an observation. It occurs to me that as we begin to place these quantum, I'll just call them quantum clocks, in orbit around or on surfaces of places other than the Earth, all of the relativistic adjustments we had to make for the first GPS satellites will have to be made all over again, because otherwise your time bases are going to drift. And it is a major problem that's being explored now by multiple agencies as we go further into space. How do we in fact determine what is time? And time between, say, Earth and the moon, or Earth and Mars. By the way, thank you very much, Anna, for putting this together, and Curtis and Rima for going through all these slides.
It was a team effort. I'm seeing Dan and Sean and Lou and others. I'm seeing NASA, ISS, SpaceWERX, Air Force folks, I think, still on the line. But if anybody wanted to add any thoughts, but I think it's just it's tremendous gratitude. I mean, the reason we wanted to bring people together today is there's so much opportunity, but there's not always the visibility into what's going on. So this has been recorded. This makes it visible so that people who want to do things can see what's readily available and build off it. So many of these briefs that were shared, there's also more in-depth recordings or presentations that are available. So I don't know if anybody else. And Diane, certainly thank you so much for your leadership in really getting visibility for so many of these disruptive concepts on the NASA Convergence Aeronautics Solutions podcast. We will try to find the right way to, as we're trying to cite that in this recording, we'll add those citations, and just grateful for your work. And really, this was tremendous team effort across the interagency and private sector to get this launched. This was about 2 weeks, I'd say. Around that, in terms of from concept of there's so much happening, there's extraordinary value, extraordinary solutions, semiconductors, energy, communications, advanced human capabilities and perception, AI, digital assets, communications, just quantum, so much here, tremendous solutions, and these very high value markets in the trillions of dollars in terms of some of the existing markets for which space might bring will bring some percentage of the market that an advantage. And but we know that more needs to happen. Many more capabilities can come to the table. We see people who aren't in space coming into space from the technical expert side. And we also see that there's a significant need for more investment dollars and more funding dollars to come in. So thank you very much. And thank you everybody for all your time. Have a great evening, and we're seeing optimism about the future. We're seeing excitement, and this was a really long time to be on a Zoom. So thank you for sticking with us, everybody.
And Merry
Thanks.
Christmas, everyone.
Thanks, everyone.
Thanks, everybody. Great discussion. Good work.
Thank you.
Hanukkah too. Oh, is that Hal back on?
Oh, I've been on the whole time.
Wow, I thought you had an engagement at the end at 5.
Yeah,
Sorry.
I do. So I'm going to pop off now.
Great to
Nice
have
to
you.
see you.
Thank you.
Okay.
Thank you, Anna, for everything, and great session.
Thanks for making it great for you and others who presented, Chance.